Standard deviation is a measure of how much data values deviate away from the mean. Imagine data points as people gathered around a central spot, which represents the mean. Standard deviation tells us on average how far are people standing from that spot. For example, if the central spot is a point in a park and the standard deviation is 5 meters, most people are standing within 5 meters of that point. A low standard deviation means the group is tightly clustered close to the spot, while a high standard deviation tells us people are spread out much further, scattered all over the park. Similarly, for something like height, if the mean is 170 centimeters with a standard deviation of 10 centimeters, most individuals are about 10 centimeters taller or shorter than the average. How do we actually find the standard deviation, which is the average deviation of data points away from the mean, given a set of data like this, which represents the wait times in minutes for a space mountain? The first step is to find the sample mean here. So to find the sample mean, you're going to add all your data values here and divide it by 11 because there are 11 data points. And as you can see, the average wait time for Space Mountain is around 39.1 minutes. The next thing we need to find is how far each data value is away from the mean, which is the deviation. If your data value is above the mean, which is 39.1 minutes, then your deviation will be positive. If your data value is below the mean, then you're going to have a negative deviation. So to find the deviation, you're simply going to subtract each data value to the mean. So 50 minus 39.1 minutes, that's going to give you 10.9 minutes. And it's positive because 50 is above the mean. And for the next data value, 25 minutes, which is below the mean, 25 minus 39.1, that's going to give you negative 14.1. So that's a negative deviation. And you keep going for each data value. Because we're interested in finding the average deviation, we can't just add all these deviations here because some of them are negative and positive. If we just add them together, we're going to cancel out the positives and the negatives. So to avoid that, the next thing we need to do is to square each deviation. So 10.9 squared, that's going to give you 118.81 minutes squared. Negative 14.1 squared, that will give you 198.81 minutes squared. And you're going to keep squaring each deviation. And as you can see, now our values are all positive. After squaring each deviations, then we need to find the sum of all the squared deviations, which is going to give us 2,740.91, and this time it will be minutes squared because we squared the deviations. And to find the average deviation, which is the standard deviation, we need to take that sum and divide it by m minus 1. The reason to divide by m minus 1 instead of n is to adjust for the fact that you're working with a sample instead of a population. Remember, we're using this sample to make a conclusion about a population. So if we just divide that sum by n, which is 11, that's going to give us 249.174 minutes squared. Versus if we divide that sum by 10, which is 11 minus 1, that's 10, that's going to give us 274.091 minutes squared. And as you can see, dividing by just n is going to underestimate the population standard deviation. Because if you divide by m minus 1, you're slightly increasing the result, which accounts for the fact that you don't have information about the entire population. This correction helps to provide a more reliable estimate of the population standard deviation based on a sample. And the last thing we need to do is to take the square root of our answer. Earlier, we squared the deviations to deal with the positive and the negative values. However, this left us with a minute squared. So we need to remove that squared so that we can bring the measurement back to the original units of the data, which is just minute. So the square root of 274.091 minutes squared, so that's going to give us standard deviation of 16.56 minutes. So this means that in general, people have to wait within 16.56 minutes, more or less from the average wait time of 39.1 minutes at Space Mountain. So here is the formula for the sample standard deviation, which represents S. So the first thing again we did was to find the sample mean, that's the X bar, and then we found the deviation for each data value, which is X, by subtracting them. And we squared because we want to make sure that we're not canceling out the positive and the negative deviations. And then you find the sum of all the square deviations. And to find the average, you divide it by n minus 1 because you're dealing with the sample, so you want to increasing your result a little bit instead of just dividing by n. And then you're taking the square root to bring the measurement back to the original units of the data, making it more interpretable. So for the population standard deviation, you use the sigma notation and you will find the population mean, and the rest are the same, and the only difference is that instead of dividing by n minus 1 like the sample standard deviation, you simply just divide by n for the population standard deviation. The next thing we're going to do is how to quickly find the standard deviation in StatCrunch. So here's my data again of Space Mountain wait time in minutes. So you're going to click on Stat, Summary Stats, Columns, select the column, and in the statistics, you're going to select Standard Deviation, press Compute, and here is our standard deviation, 16.56 minutes, which is what we found earlier by hand. As we end this video, please keep in mind that the standard deviation can never be negative and it's only 0 if all data points are exactly the same. A larger standard deviation means the data points are further away from the mean, so this indicates that there's going to be more variation or spread in the data. A smaller standard deviation means the data points are closer together near the mean, so this indicates there's less variation. Since standard deviation calculates how far each data point is from the mean, an outlier can significantly increase the standard deviation. Therefore, we can say that the standard deviation is not resistant to extreme values. And the last thing is that the standard deviation is always expressed in the same units as the original data. That's why we took the square root from the formula at the end.